Okay, we're good to start. Welcome everybody to the 8th EasyBuild Tech Talk. It's been a while since we've had one, but this one in particular should be a very interesting talk for a whole bunch of reasons. We have Felix LeClair today who will be talking about AVX10 for HPC. So the floor is yours, Felix.
Thanks. So AVX10 for HPC with the loose title, A Reasonable Solution for the 7 Levels of AVX-512 Folly. You're going to detect a little bit of a theme of light humor, a little bit of sarcasm here and there, but fundamentally, we're sticking to the world of x86 today. So x86, x64, that's Intel Xeons, that's AMD EPYCs, and a little bit of consumer platforms. We're going to be taking a historical view as well, going all the way back to the 70s, for which some of the people in the call, yours truly included, weren't even around, and then building our way up from all those legacy instruction sets to understand where we came from for why we are where we are today. And then along those lines, there's going to be an understanding of what are we covering, where we came from, but also why we got to where we are in terms of the way it's implemented, right? Because one of the things we're going to be talking about a lot today is what's an ISA, so what's an instruction set architecture, what's an extension to that, and then why we got what we got, because a specification without an implementation is just a piece of paper that you can throw and chuck in the bin, kind of like a paper that no one ever read. It doesn't actually move much of anything forward. So the first question is, what is an instruction set architecture? I asked around to a lot of folks, some of which are more private, some of which are more public, some of which designed AVX-512. And I got a bunch of different answers. But one of the things that you're going to see clearly in all of these kind of quotes is it's the language that at the fundamental level, your computer interprets. We read it as assembly language in a sense, but fundamentally it's the instructions and how those are specified. So when you say, I want to do A plus Y, well, you need an instruction to do that. You also need to say, okay, what registers are those in? If you're doing floating point, you need to define what the rounding behavior is. But fundamentally, it's the language of the chips, right? And this ISA is a mapping between integers. So what you see as an opcode or an operation code, the hex and binaries of computers, to things that programmers can understand. It's a vocabulary. I thought one of these was particularly cute. An ISA is like a musical note. It makes an orchestra of transistors perform a symphony of compute. Then Andrew Richards, CEO of CodePlay, now owned by Intel, put it particularly well as well, where is a contract between hardware and software designers to let us work together. This is supposed to be Steve Cannon of Apple. For higher level programmers, an ISA is the stable API for the CPU. And then this is a favorite. Tom Forsyth, unofficially the father of AVX-512, put it best. An ISA is the train line to which hardware designers chain their screaming future colleagues to. And that's because fundamentally, when you have an ISA, when you have an instruction set, you're mandating that all your chips implement it. But once an implementation is out in the wild, once you have those instructions, that's software. You can't change all of your software all the time, right? So once it's in, your chips have to support it. So if you mess up during the design phase, well, you're just stuck with it. You just have to accept it and move on. So that's kind of our intro. Section 1 is when we had ISAs from the 70s and the original 8088, the original 8086. And there you had floating point numbers or SIMD, right? And we'll get to more of what SIMD is as we move on, but floating point, I think everyone here is familiar. So talking about the original ISA of x86, it's not going to solve all the problems of today, right? Something designed in 1978, trying to look forward to what's going to be useful in before the IBM PC even existed. That's what the original 8086 did, right? It was a small 16-bit microcomputer which used an internal 8-bit bus to save on costs, right? And the parallels with that are similar for HPC type things to Fortran 77 in a lot of ways, where Fortran 77, when it came out, was great, mind-bogglingly advanced, right? Did a lot of really good things for the time. But ask someone today to write Fortran 77 instead of, say, Fortran 2018 or something like that, they're going to look at you like you have 3 heads. Like, no, it's not happening. So the original 8086 and the 8088, which were the test, more of a small micro-embedded chip, and then finally the 8088, which became the IBM PC, they didn't have support for floating point. They just didn't. So if and when you went to do any maths at that point, whenever you needed to do any division algorithms, well, that algorithm is n squared, and have fun, right? So we're going to be looking at some code today. You don't need to have written a lot of C. You don't need to have written a lot of assembly to understand what's actually going on here. So what we're doing is, everyone who's written a lot of HPC codes, or even a little bit of HPC code at the high level, we're going to be looking at how do you implement a basic AX plus Y in double precision function. So the idea is, so if you read it, perform DAXP, double precision AX plus Y. So function to add the elements of 2 arrays. We have a function. It's C/C++, but everyone should be able to understand it. We're taking in an integer n, so how many things we're doing. And then basically we have 3 arrays. And then we're going to loop through them. So a do while I smaller than n. And we're going to look at that and say that z is going to be updated to have the value of x plus y multiplied by z, right? A simple ax plus y. And then int is just the main is stuff that you do in CS 101 class 1. Now, if you look at the actual code here, in terms of the assembly, you're going to see a lot of moves and pushes and calls and so on. And then a few adds and a few movement instructions. And essentially what's going on in that code, and you don't need to read all that, the important part to get here is that we're having to simulate and loop through all of our floating point operations, because we're dealing with floating point numbers. And to the surprise of no one in HPC, we actually care about the decimal point, for which floating point is a really good idea. So realizing this, in 1980, we got a new it wasn't, at that point, it wasn't an ISA. It was actually a coprocessor called the 8087, or lovingly referred to these days as the X87. And we got floating point on X86 before it was called X86. So that coprocessor, that X87, supported 3 major data types. It supported FP32, or single precision floats, double precision, and FP64. And it also supported this weird FP80 type, which never went somewhere, but that we're still stuck with today because, as is the theme, it existed and software used it because it was useful at the time. So now we have to live with it. And one of the things that happened with the 8087 is that under the hood, even if you said, oh, use an FP32, and you're only using 32 bits of your 80-bit register, it actually would extend that FP32 to an 80-bit, which means that if you go to compare a 32-bit float edition today to the ones that you got from the 8087, you'll actually get different results, because the 8087 was doing everything in 80-bit floating point precision, right? So you'll actually get different rounding behavior, different offset behavior, and so on. But one of the things that the 8087 did really well was it inspired what would become the Bible of floating point for the modern era, right? The de facto specification is IEEE 754. Then it was just IEEE 754. Now it's IEEE 754 1985, and then there was a 854 87 spec for decimals. But the long and short of it is, if you have binary representation of floating point numbers, it uses IEEE 754 as amended. So here's where things get kind of cool. On the left, you'll have the same code as before. And now you'll see all these little F loads, or F adds and F multiplies, right? And F store pointers. FSTP is F store pointer. And the idea here is you're looking at it, hey, with a single instruction, I can do my add, I can do my I multiply, I can do my loads and my stores. I'm not having to extend, I'm not having to do any shifting behavior, I'm not having to dissect parts of my floating point for what part of it is the exponent, one part of it is the mantissa, so on and so forth. And then you're just looping through that. And it's significantly faster, orders of magnitude faster, in fact. Now, At that point, we were doing one instruction at a time and one data type processing at a time. Remember that part I said where FP32, you would use that in a whole 80-bit register? So your entire floating point unit, you have 80 bits, but you're only doing 32 bits worth of compute at a time. It's not really efficient. Those days, we had other ideas for how to get around that, but it wasn't this popular concept. Then comes along Intel in 1997. So 17 years later, basically half of people's careers. And they introduced this thing called MMX, or the multimedia extensions. And the idea here is that you have 4 data types, in64, 2 in32s. 2x something. Why would that be? The idea was we're going to use the register file, the registers from the 8087. But what we're going to do is we're going to put multiple pieces of data in those registers at the same time. So let's say that you have a loop that's doing the same thing to multiple pieces of data. So you could say that you're doing the same instructions at once, but then you're doing multiple data points at the same time. And so long as, say, you're looking at a linear loop and expanding, as HPC often does for when you're looping through massive arrays of data, you don't have a data dependency between entry 1 and entry 2 in the same array, right? So what you can do is have one instruction compute multiple of those at the same time. Now, with MMX being multimedia focused, and especially back in 1997, and them wanting to reuse the 80-bit registers of the 8087, fundamentally, no floating point. Okay, we use the same register. We can interleave some floating point and some integer operations, but you're not doing all that. So you have to choose. Are you doing SIMD or are you doing floating point? And then here, if your chip supported MMX, well, MMX doesn't support 64-bit floating point. So you end up falling back on the 8087's floating point unit. So your code looks exactly the same, right? It's identical. So even though your chip is 17 years newer, or even newer than that, you're still relying on the floating point behavior from nearly 2 decades ago. Your chip's a lot faster because at that time we were just adding larger floating point units. We were getting more chips and running them significantly higher clocks. But fundamentally, your assembly, your actual code, your actual operations are doing the same thing. A little bit of a Spider-Man meme in there because your code is identical because you can't use MMX to do any of your DAXP operations. Well, that's a little bit silly. So what if we did floating point and SIMD at the same time? Now you're cooking, right? Then we get SSE1 in 1999. The streaming SIMD extensions, because we love having nested acronyms within everything. SSE1, however, only supported one data type. It added new registers, and they were 128 bits wide. But fundamentally, it only supported 32-bit floats. They were IEEE 754 32-bit floats. But for HPC, especially then when we weren't as worried about memory bandwidth and going to lower types because of that, it just wasn't all that handy, right? You could do some algorithms to use FP32 SIMD to approximate FP32 or FP64s and shift between them, but honestly, it just wasn't worth the headache. At that point, once again, historically, when you were looking at chips, we were doubling the frequency every few years, right? Moore's law was well and truly active at that point. It made more sense to just wait a year and expand your cluster than it did to, we're going to do some really weird assembly stuff. But then the year 2000, the new millennium, we get SSE2, streaming SIMD extensions 2, and we finally have a real general purpose SIMD. Overall, SSE now supports 2 FP64s at a time. We're doubling the size of the floating point unit. And we're also, because we're no longer relying on the 8087, we're never falling out of specification because of rounding behavior of the 80-bit internal floating point. We now have consistent, reliable 64-bit floats across our chips that implement this. And then, of course, you have, because the idea was same instruction, multiple data, they also make it more general purpose. So yeah, we have our or FP32s from SSE1, but we also now have integer operations, which on the more consumer side of things, or for say large loads of data, was really handy. So now this code looks a lot bigger, but the idea here is if you jump to where in red you'll see XMM pointers, right? Here we basically have two loops where you see all those quad word pointers, XMM word pointers. The idea here is that you have one main loop that does two of the FP64s at a time. You're adding packed doubles together. So you'll see add PD, that you're doing the add operation, you're adding two numbers together. And then the PD is packed. So one register, multiple pieces of data inside. And then within that, the D is doubles, so double precision numbers. The problem here is that you don't always know when you read, when you're running near the end of your array, if you're going to be aligned on having an odd or an even number of data points. So at some point, you might have only one left. And when you're writing general purpose code, you don't know what you're going to run into. So if you look to the right of the XMM word, so bottom of column 2, you'll see a lot of the same instructions as the one on the left. But instead of being the packed variants, these are the single variants. So add SD. So add a scalar double register. So this means if you have one trailing at the end, well, you have a tail loop to handle the residuals. When you only had one of these entries, not a big deal. But when we get up to bigger and bigger registers, which we will, that becomes more relevant. A note here on compilers, for package maintainers, for people deploying software. You may have heard optimization engineers, research software engineers, people that want to make your code go fast for you, talk about make sure you tell your compiler what you're running on. Because fundamentally, SSE2, which is also when we went from 32-bit to 64-bit on x86, is still the default target. Still, today. Remember that part about code and so on designed in the mid-70s was not great for stuff we're doing today? Well, by the same token, why are you targeting an instruction set that is now 23 years old, that's old enough to vote and so on, and drink everywhere, right? Come on. So fundamentally, make sure your compiler knows what it's running on, right? When you, your users, your packagers, or your libraries don't provide an march or telling the compiler what architecture you're targeting, the default is to fall back on SSE2. And I might get some guff for this, but it's hard to believe it. Technology has come a long way since 2000, right? So it doesn't feel like it sometimes. I'm here talking in 2023 as a 26-year-old guy talking about assembly language. That feels like straight out of something from 5 decades ago. But technology has moved on. So we go on, and 2004 rolls around. And we have the streaming SIMD extensions version 3 in 2004. Really cool instructions. It's like a at this point, add XMM1 and 2 is horizontally add packed doubles. So the idea here is instead of two registers on top of each other going vertical in your pipeline, what you're actually doing is you can say, okay, I have this register of 2 data points. I want to sum those. And then I have this other register, and I'm going to sum those. And then I'm going to store them in one register. So you can see how this can, especially like a really common application for HPC these days is things like artificial intelligence and so on. And one of the applications that those rely on a lot is an all reduce application, where you're basically summing up and multiplying every single part. And you can do this for your matrix decomposition as well, where you're summing and then you're bringing together. This doesn't help for a DAXP example, but something like it will. SSE, and that thing that will is SSE 4.1 and SSE 4.2 in 2004. Here we get dot products. Oh my gosh, which for some of you might be familiar, a dot product is fundamentally the same operation as a fuse multiply add, which in turn is the same as AX plus Y, right? So here, 2004, we have dot product of packed doubles, where you're taking two registers and then this thing called an immediate 8, basically a control register to say, hey, if it's this value, don't bother multiplying, just pump it straight through the register. Now, when it comes to software, you'll notice I said the default earlier for SSE2. Because we never know exactly what implementations are, and we don't want to target all of AMD and all of Intel and all of VIA and all of Centrix and all of Centaur all at the same time, all these different x86 minor and major vendors. The folks at Intel, Red Hat, and I think it was Oracle came together to say, we need a specification for general purpose versions. And they decided that version 2 would be everything up into and including SSE 4.2. So that means a generic CPU that has all the way up to the SSE 4.2 instructions. Basically, that includes everything since 2013, including, say, a really tiny embedded microprocessor inside of a set-top box. That's going to be running SSE 4.2. So in terms of our DAXP example, this is going to be important. I do want to have a quick note here. SSE 4.2 wasn't as clean as it looks. At that point, people were realizing, after not having extended the instruction sets for a long time between the 1980s and the 1990s, it became the thing du jour to just add more extensions and add more extensions and add more extensions. So there was a lot of experimentation that sort of made it into the market, but never caught on. So I'm just covering all my bases here. So AMD came out with their 3D Now extensions that use the SSE registers. We had SSS E3 that did a few interesting things. SSE5 was another one where it was trying to treat more underlying questions of floating point. Sorry, I'm just checking for time here, etc. None of them survived to become anything particularly relevant. But one of the things that did happen at this point is that when we moved, as mentioned, to 64-bit operating systems, we doubled the amount of registers we had. We had 8, now we have 16 of those registers. You can thank the fine folks at AMD for that. All credit is due. When Intel was trying to bring us down the Itanium route, that was a bad idea, universally accepted at this point, and we moved to AMD 64, better known these days as x86 64. So I do want to take a very brief pause here. That was a lot to get through and very quickly. Do we have any quick clarifications? Not more questions for the end, but just quick clarifications of high level.
If you do, please raise your hand in Zoom or post a message in the Tech Talks channel in Slack. I'm not seeing anything popping up, Felix, so I think we can continue.
Yeah, that's great. Perfect. So let's go on. So section 3, advanced floating point, same instruction, multiple data, or advanced floating point extensions, AVX, advanced floating point. So here we realized, hey, CPUs are starting to really, especially x86 at the time, is really taking off. We're not doing our Sun microsystems anymore. We're not doing our Cray Vector and our Cray Vector processors. Tsubasa from NEC is less and less of a thing. So as a general purpose processor, we're also doing compute on them at this point. So AVX1 in around 2010 comes on, the advanced same instruction multiple data extensions, targeting mainly HPC. And here what happens is we're still at 16 registers, but we're jumping to double their size. So instead of 2 FP64s, we now have 4 of them. If you're doing single precision math, you now have 8 of them. But the thing is, this is something that Intel could do relatively easily at the time because they are a CISC, a complex instruction set computer, versus the risks that you see with ARM and RISC-V and MIPS and so on. So they can just really expand the entire instruction set, and not only expand it, but say, hey, we want to do a lot of really interesting things. We need an extra byte on our instructions. And that was the introduction of VEX, the vector encode. It's not officially called this, but the vector encoding subset of x86, where they added an extra byte as a prefix on the instructions. And then suddenly, hey, we can address twice as many registers, right? They can be twice as big and so on. And when you look at the assembly for these sort of processors, targeting them, when you make sure to turn on your compiler optimizations for those targets, you'll notice a lot of add packed doubles becomes V add packed doubles, or vector add packed doubles, vex add packed doubles, right? The big thing is the V means, hey, we're dealing with larger registers, or we're dealing with a more advanced instructions in the first place. Most of the time it's both. It's always one of the two whenever you see the V. So here, you'll notice compared to our loops from earlier, on the left, still the same code. On the right, you're seeing these vmov unpacked doubles, YMM0. So here what's happening is the compiler is unrolling our code, so unrolling our loops, and then prefetching all of our memory at the same time. So not only are we doing more math per iteration of our loop, the compilers realized, hey, memory pressure, memory bandwidth is a problem. So what happens is I can use these larger registers to just do a single read of memory at the time. So instead of loading one FP64, another FP64, another FP64, another FP64, just for my add, and then doing the same for my multiply, so 3 times that, you can say, I just want one load, one instruction to grab everything. And then at the same time, we're realizing is, hey, we're what's known as an out of order execution CPU. So your actual instructions underlying your chip, we don't have to execute them all in order, which means that we can do a lot of prefetching. And while we wait for that memory to arrive, we can do the compute for another part of our array and another part of our kernel, right? You can do these things simultaneously and change the order, because fundamentally, df times dx. Yes, sorry, I'm looking at the chat. It's not technically DAXV. It's close enough for everyone here. If you're writing BLAS libraries, yes, we can chat about that. Anyway, fundamentally, we are doing larger vectors. And that was great for HPC, but fundamentally, x86 is not only an HPC target. At the end of the day, we're actually targeting a lot of consumer, a lot of general purpose enterprise, a lot of data center applications. And to the shock and dismay of everyone, including yours truly, not everyone does everything in 64-bit floats. So AVX2 comes along, Advanced ND2, Electric Boogaloo, keeps those 256-bit vectors, and then expands that to be 6.5 data types for your registers. The half is important, gets to what I work on personally. But we still have the 4x FP64s, we still have our 8 FP32s. But now, instead of relying on SFC for all of our integer operations, now we have 256-bit vector support for 64-bit quad words, 32-bit double words, 16-bit words, and then our bytes. And you can do 32 of them per iteration array. That's a lot. That's a lot. And then I'd be remiss if I didn't mention the 0.5. At this point, between AVX1 and AVX2, we had a generation called Ivy Bridge. And with Ivy Bridge, Intel implemented this thing called F16C, which was floating point 16 conversion. And the idea here is that IEEE had finally updated the floating point spec in 2008 to add FP16 as an official specification. But at that point, everyone was like, you can't actually do anything in FP16 for actual arithmetic. But it might be useful if we store floating points. So that way, because you have a defined definition for what converting an FP32 to an FP16 looks like, hey, we can convert between the two. And then to save memory bandwidth, what we can do is we can have all of our memory be FP16, load all of that into our registers, convert that to 32-bit, do all of our math at a higher precision for our time steps. And then from there, once our math is over, we can go and we can store that back to memory as FP16. But Fundamentally, you can't. Also, at the same time, to F16C, we get fuse multiply add instructions. And the fused multiply add is interesting because it's like the dot product instructions from earlier, but you're actually doing it in one step, and you have a higher internal accumulation precision. So you don't lose anything because you're doing it in 2 steps. You don't have 2 rounding steps like floating point normally has. So here's our assembly and our code. Once again, you're probably getting familiar with this. And if we once again go to the YMM pointer part, you'll see VMOV on the VMOV is basically memory prefetching. But now we're using YMM 0 all the way to 7. And those are there to do all of our memory caching. And then we have this VF-MAD 213 pack doubles, which is a little bit head scratcher. A vector fused multiply add registers 2, 1, and 3 of that contain packed doubles. So what's cool here is that before we were always doing do your multiply, then do your add, right? Or do your add, then do your multiply. Whereas here, we have one instruction and it's taking in 3 pieces of data. You can never do that before, right? You could do 2 floating point registers with packed data and then like an immediate integer, like a little 8-bit thing. It's not all that useful. But here we have 3 full-fledged 256-bit registers coming in at a time. And once again, because of things like the branch predictor, the out-of-order execution engine, because we know this fuse multiply add instruction is coming, we can go and do the memory prefetch transparently in the background. So we only effectively do our memory prefetch for 2 of our operands. And then when the instruction comes, we're just in time to fetch the 3rd operand for that instruction. Now, once again, these are really big vectors, right? We're storing 4 FP64s per register. So on the right side, you'll see we're still using those VF mad instructions or the very mad instructions. But you'll see it's SD instead of PD. So it's a scalar of double precision. So basically, we only have 1 entry in our loop. And that's just to make sure that we're not fetching memory out of bounds. We're not accessing something we shouldn't be accessing. So it's, oh, now we can decrement the last part. You'll sometimes, it's not quite the correct term, but you'll sometimes see this referred to as tail latency or the tail of a multiply instruction stream. So it's worth at this point comparing the 2. So you'll notice the top part is nearly identical. The end is nearly identical. But when we're doing our actual math, hey, we're doing some prefetching here, some prefetching there, but we're actually combining all of those instructions into a single instruction. And when you look at the actual implementations of these instructions on the actual CPUs running the math, you'll see each multiply instruction was typically like 4, maybe 5 clocks. And then that add instruction was another 2 clocks. But something that CPU designers did that was really clever is that they essentially made it so that the fused multiply add variant of these instructions was actually using the multiplication floating point units. So you actually got the add for free once you did this. So you actually cut your execution time to do the math by 2/3 to 4 to 6 instructions total for your fuse multiply add, instead of 4 to 6 for the multiply and then 1 or 2 for the add itself. My math was slightly wrong there, but you get the idea. And then just to break that down a little bit more, just so it's a little bit clearer, we have our main loop and we have our residuals. We have our main loop and we have our residuals. There you can really see vector fuse multiply add of pack doubles. So once again, you'll notice earlier I mentioned we have levels so that you can generically target devices. Targets that implement all the way to AVX2, including FP16 and FMA3. FMA3 is the actual instruction set for 3 operand fuse multiply add, are considered x86-64-V3 compliant. The important thing about these flags is that they're recognized by your clangs, by your GCCs, by your ICXs, your AOMPs, and so on. They are generic compiler levels that you can pass your compiler to, once again, make sure you aren't stuck on instructions from the year 2000. And this is pretty much every HPC CPU since 2014. There's a few weird embedded chips for, once again, like set-top boxes that don't have AVX2 or AVX, but this is an HPC talk with a mostly HPC audience. For all intents and purposes, you yourselves can always put x86 64 v3. Maybe not in your home labs if you're running some really old, say, Sandy Bridge era Xeons, but they don't last forever, guys. One thing here is that it doesn't include tuning. So once again, we're looking at the specification of does it support it, not how does it implement it. Just a side note there. So once again, that's a lot to get through. I wanted to open the floor for any quick clarifications.
So again, if you would like to clarification here, please raise your hand in Zoom or speak up in the Tech Talks channel in Slack. Well, it looks perfectly clear and certainly is to me, Felix. So
wonderful. I realize that, especially looking at assembly, for those unfamiliar, can be a little bit intimidating. So I always want to provide the option. We are rapidly running out of time. Good Lord. Okay. So section 4, larger advanced floating point SIMD. So this is where the title of the talk came in. AVX-512 or the AVX10, a solution to the 7 follies of AVX-512. AVX-512 came along, and we're going to talk about it. But fundamentally, it did a lot of things. But one of the mistakes it did, in my opinion, was not requiring contiguous supersets of all previous instructions for your implementation, which meant that you could pick and choose what instructions you added that were from AVX-512, which means that when you go to support all these different AVX-512 devices, you end up with this mess of somewhat overlapping, somewhat superset CPUs and supported instructions, not all of which were supported at the same time, many of which came out at the same time, same years, and were also all, say, Xeon 3rd generation or Xeon 2nd generation, but didn't support the same instructions. So you could have one center in the States that bought 3rd generation Xeons, and then one center in, say, Belgium that bought 3rd generation Xeons, yet those 3rd generation Xeons can't run the same code, right? And we'll go through all these various things. One of the things you're going to see is AVX. I'm going to refer to AVX-512, not as AVX-512. I'm going to be referring to it as AVX-3 to AVX-9, because that's sort of what happened. It's not quite true, but it's close enough for, unless you're actually writing an instruction set architecture. Other note, I'm ignoring Xeon Phi. Xeon Phi is a really cool device, but Phi and Larrabee just aren't relevant for the topic of discussion. They're good for historical context, but they're just not relevant here. If you're interested in what became Phi, what was the Larrabee project at Intel, I highly recommend Tom Forsyth's talk, Smack Me to AVX-512, the life cycle of an instruction set. The links are in the extra detail, extra resources on the EasyBuild landing page for this talk. Really interesting stuff. We just don't have time to cover it. So AVX-512, the original version, aka what I refer to as AVX-3. Advanced SIMD 3, big vectors, look at me. So what we're getting here is, you may remember, AVX2, we were at 16 256-bit vector registers. So these are already pretty big, and that's a lot to keep track of every time you're context switching, for example, right? But AVX-512, in its original form, AVX3, gave us 32 registers and also doubled them. So we're getting 4 times as much total bits for our registers. And the original version supported 4 things. It gave us 8 FP64s, 8 double precision floats, 16 FP32s, 8 times 64-bit. You can read the slide. You're all smart people. I'm sure you're literate. So But the big thing here is we have more registers to do our math and store data and do our prefetching with as well. But I said I'm ignoring phi. I'm ignoring it because AVX3 itself never ended up in a single chip. What I would consider real AVX512 or version 4 added a bunch of other extensions to make it actually viable in a big CPU and something you could actually install. Specifically, right now, we're looking at a die shot from Skylake X, the 10-core variant. So there we get we add on top of what we already had, we add 16 times 32-bit integers, 32-bit unsigned and signed integers, and 64 times 8-bit integers and unsigned integers. You'll notice throughout the talk, I was talking about integers, but we never had the unsigned variants. Well, finally, AVX512 brings that to the table. But fundamentally, for HPC, it's more of the same as AVX1. We still have fuse, multiply, adds, and we have bigger registers. Great, we can do more math per cycle. So at that point, let's look at that. You'll notice at this point, it's pretty much the same as before, but now we're looking at ZMM or ZMM registers, depending on where the world you're from. And the idea here is that these are the same registers as our YMMs, which are actually the same registers as our XMMs. We keep just expanding and making them larger and longer and adding more of them, right? But in terms of our actual instructions, we expanded them from VEX to extended VEX or EVEX, but they're effectively the same, right? We're running the same sort of instructions. Then we got version 5, which was originally Cannon Lake, but that Cannon Lake never really took off. It did some really cool things with instructions, though. It's essentially one data type called the integer fuse multiply add. To your point, Kenneth, that's actually because the A, the B's, and the C registers were used for the main general purpose registers. So we went to the opposite side of the alphabet. But anyway, so here what happened was, hey, if you actually take a look at the underlying structure of a floating point, 52 bits of a double precision floating point is actually just an integer, right? And there are applications, say like signal processing, Fourier transforms, and so on, where it can be useful to do everything in integer maths. But at the same time, we want as much precision between steps, so that would be your multiplies and your divides, as possible before any rounding from the integer side, right? So what happened here was they said, you know what we can do is we can give you an integer version of these big floating point units. And now it's a 52-bit integer, and it uses 104-bit internal accumulation. Kind of cool. And then VBMI was vector byte manipulation instructions, which just aren't relevant for HPC. They're useful for some kind of lower level data processing applications, signal processing stuff, but it just wasn't relevant for HPC. AVX512 version 6 came along. And here's where we're looking at, it's the age of AI in HPC, where the big AI folks are running a lot on GPUs, but when they need to run big clusters, they need the memory, and they just want to process on their actual CPUs. So Intel came along and implemented what's known as a brain float, which is fundamentally the same as an IEEE FP32. It's the same thing. But what happens is AI cares more about the range, which is at the front of your data type, less about the precision. Who knew AI was not precise? Shocking, I know. But fundamentally, you're truncating. And after that, all of the rounding, all of the other considerations of brain float are the same as FP32. So they added this. Cooper Lake had a limited installation market. It was mostly the big cloud vendors, those folks. So AI firms using HPC love this, but classical HPC, where it's floating point or it's nothing, maybe a little bit of single precision, just wasn't relevant for us. We got version 7 at that point, which was not any data type expansion. But what we did get at that point was integer FMA for unsigned integers and signed integers for 8-bit and 16-bit. So for those looking, once again, I feel like I'm talking a lot about AI, but that's what the conversations are these days. When you're looking at inference workloads, so you've trained your model and now you want to deploy it, there's something called quantization, where you trained an FP32, but you don't want to do all that level of math for single time steps. When you're looking at thousands of time steps, you need the precision of a big floating point unit. But what inference in AI workloads does is we're only running one epoch, right? We're only running one more time step of our model for the most part, details. So what happens there is that you can reduce everything to their bare minimums with 8-bit. And then that's where VNNI, or the vectoral neural network instructions, came in, where you had these little tools. And there you had AI using HPC, used it for CPU inference, whereas BrainFloat was more for training the model in the first place. And then VBMI2 was expanded some of the vector byte manipulation instructions. And then beyond that, bit algorithms were things like population counts and other very low level manipulations that just, once again, they're just not relevant for HPC. AVX512 version 8 would be VP2 intersect, and this one's actually since been deprecated. I asked around a lot because it looked like it wasn't happening anymore. And then Ronak Segal from Intel helpfully commented on one of my tweets where I was asking what the heck's going on with this, and said, no, it's deprecated. Or yes, it is deprecated. So this one isn't super relevant, but it was its own discrete generation. Version 9, finally, floating point numbers. Yay, HPC. So here we get 1 + I data types, because floating point 16 never does anything the normal way. We had to get a half data type support for storing, but not for adding it. Now we get it in full. So now we get IEEE 754 compliant binary 16, and we get to add it, we get to multiply it, we can do whatever we want. With that, it expands even beyond what we had with FP64 and FP32, where we now get dedicated complex plane instructions for encoding. So for things where you're doing transforms in and out of the complex plane, instead of having to do data manipulation steps, so some exponents and so on, you can actually do that all in one instruction. So now not only can you use it for data processing and for some lower level precision stuff, so say the store and then expand stuff I was talking about earlier, but some kind of higher level edge maths can be done completely in FP16. Excuse me, a lot of talking. So that was version 9. So as of now, once again, with our generalized target that your compiler can actually use, if you implement all the way to AVX512 F foundation, BW, byte and word, CD, conflict detection, used for unrolling loops and conflicts and so on, DQ, which is double words, quad words, and VL, which is vector length, which means that your AVX512 instructions can run on your big 512-bit registers, but they can also operate on your 256-bit and 128-bit registers. You have all of those things, which is approximately version 3 and version 4 together. Those are considered x86-64 version 4 compliant. That's basically everything in HPC from Intel since 2015, AMD since Zen 4, which is sort of started seeding to some labs and some users in 2021, but actually made it into general production in 2022. And I think there's 1 or 2 people in the room that got to mess around with Centaur's AVX512 implementation. It doesn't matter. I'm not going to talk about it, just like Phi. But the long and short of it is that you have really powerful data processing and lots of massive vectors. So AVX10. That was a lot about AVX512 for a talk that's about AVX10. What in the world is AVX10? Section 5, no more subversioning. So subverting expectations. The goal of AVX10 is to put an end to this. I hope AVX512 dies a painful death and that Intel starts fixing real problems, blah, 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 blah. Famous Linus Torvald's quote about why he thinks, especially at the time, that AVX512 should die, because at that point it was purely an HPC thing. Normal people weren't getting much value out of it, because you could only have AVX512 on these big, large systems and these big, large CPUs for the longest time, right? 32 times 512-bit registers doesn't sound like a lot, but supporting that in your floating point units, supporting that whenever you have a context switch and then need to store, like load and store those registers, that's really expensive. And that's hard to do in a small laptop CPU that's supposed to only draw like 5 to 10 watts. It's just really hard to do. And the goal of AVX10 is also to put an end to this, where this is from YCruncher, the pi and other kind of mathematical constant benchmarking application, where you're having to detect, okay, I have the foundation instructions, I have the conflict detections, but I don't have the extended reciprocal instructions, and but I do have the variable length instructions, but I don't have the 4 input fuse multiply add of pack single instructions from Xeon Phi, and on and on. And it's meant to take an end to this, which is some code I wrote for like a little benchmark application where you're having to individually test every single flag for, hey, do I have AVX at all? Do I have SSE? Do I have AVX-512? Do I have AVX-512 FP16? Do I have just the FP16 conversion instructions, right? You're having to do all of these routines one at a time for your optimized BLAS library or your optimized LAPACK library, just to see, hey, I think I have this chip, but I need to check every single flag at runtime and at compilation time to make sure that I can actually run this code. Because the last thing you want is a user walking up to your cluster and that cluster just giving you an error. That's not fun. And the last thing we want is for that to happen. Users deserve better, right? So that's why we have to do these routines, but these routines are a pain in the butt. And then this is from OpenBLAS, where this is this is like 1/10 of the detection code for figuring out what chip we're running on. And we're doing it by detecting what instructions it supports. And then later on, it's like, oh, is this Alder Lake desktop or is this Alder Lake mobile? Or is this Skylake X or is this Cooper Lake, right? And this from Jeff Hammond, formerly of Argonne, then at Intel and now at NVIDIA, where it was an entire suite mass deployed in open source for detecting what's on my chip, what AVX-512 does it support, how many fuse multiply adds does it actually support, right? I think you all get the point. AVX-512, because of its nature of not being a contiguous superset, ends up where it's spaghetti and you never know, and you can never trust what you actually have. So you end up with all this extra infrastructure code that is always spaghetti because you're always having to re-implement it every time something changes and something gets added. And if you don't get it, it's I don't know what to tell you. So AVX10, answer the darn question. What is it? AVX10 is actually AVX10.n/m. Okay. Okay, I know. Give me a second. We're going to get there. What does the point n in AVX10.n/m mean? Simple. It's actually really simple. N is version number. You have AVX10 version 1, 2, and 3 in the future. Period. Something gets added, you increment. Importantly, if you CPU says it supports n+4, so let's say version 5 down the line, that means it supports version 4, and it supports version 3, and it supports version 2, and it supports version 1. Guaranteed. You don't have to think about it. It just supports it. Clear supersets. What does the M in AVX10.n/m mean? Simple. M is implementation size of your vector registers. Valid options are 512, 256, and sort of 128. I'll get to the 128 later. But by and large, you'll notice earlier I was talking about how it's a lot of state to keep track of, right? 32 times 512-bit vectors is a lot for a consumer CPU or a little embedded chip that's going on a small little robot. It's just not going to work. You don't have the power, you don't have the space to implement what you want to implement here. So you're making a small chip, do the 256-bit version, period. And importantly here, if you have code for 256-bit AVX10, as long as you're at the same version number, or your code is compiled for the same version number, your 512-bit CPU will run that code all day long, no questions asked. The same way that all AVX2 CPUs can run smaller SSE4 codes. Okay, what does it include? Version 1, which is the only version that's out so far and that we know about publicly, is all of AVX2, which implies all of AVX1, which implies all of fuse multiply adds and SSE 1 till 4.2. And all of the instructions from AVX-512 foundation, conflict detection, variable length, double quad words, byte and words, integer fuse multiply adds, vector byte manipulation instructions 1 and 2, population count, bit algorithms, vector neural network instructions, the long one, Galois field neural instructions, VAES, BF16, and FP16. We have all the instructions from those generations, but not the 512-bit vectors. The italics and asterisks on that last slide are very spooky on today, Friday the 13th. So what's up with that? Because AVX10 is meant to allow instruction support on smaller chips, it keeps the instructions from AVX512, but not the register sizes. Isn't that just going to go, talking to people about this before this talk came about, it was like, isn't that just going to make things worse? And like all things in life, yes and no, it depends. It does mean you can run a single check and know what is and isn't supported. Great, less spaghetti code. It does mean you need to check for local implementation size. Fine. But it does mean I'm checking 2 things instead of checking 9 different things and trying to build a tree of what that does and doesn't imply for targets. It's a good thing. Say it again. Most of the instructions from AVX512 are great for commercial data center as well as local client data processing. They don't do much for classical HPC apps, right? But we're not the only people in the industry. We're not the only people using computers, right? So AVX10 for HPC, beyond the spec, what is it? For admins and users, it's a single compiler flag to enable all of the goodies in the history of AVX512, right? For programmers, developers, research software engineers, etc., it's a pair of CPU ID flags that you can check in your assembly functions to check for kernel version and targeting and implementation size. Kernel here is a fancy math/library name for what your BLOS function is actually like, right? Underlying. It's not the Linux kernel or the Windows kernel. Name overloading is fun. This is another case of that. Is it out? Yes. Section 6, AVX10 for HPC in 2023. So AVX 10.1/512 is coming officially next year in silicon with Intel's Granite Rapids Xeons. They've been public about this. It's coming soon. But that's next year. I don't care how, I want it now. Good news. AVX 10.1/512 is the same from an instruction set standpoint. So the actual binary instructions as Sapphire Rapids, so Xeon 4th generation, and the upcoming retooling of Sapphire Rapids known as Emerald Rapids, which is coming out in December per Intel. For those with Intel Dev Cloud or that are affiliated or have access to Argonne National Laboratory / Argonne Leadership Computing Facilities Sunspot supercomputer, which is a subset of Aurora, your codes for SPR are the same, I say, as AVX512 or AVX 10.1/512. They'll run the same. That's all, folks. I do want to have some brief notes to add some content here, some context. AVX10 256 are coming soon. I personally expect this isn't under NDA or anything like that. It's just from kind of what I've been watching on the mailing lists. I expect the 256-bit version, so for your developer laptops that you'll be deploying across your fleet for the IT managers in the call, probably in 24. And I expect AMD to support AVX10 in general, 512-bit, in probably 25. Brief note on AVX10/128 in general. Yeah, I'm at time here. So AVX10/128 is a silly, silly, silly idea. It should never have been allowed to exist. And I've actually asked Intel formally to remove it from the specification. I wrote an entire companion article that was originally slated to be part of this talk, but there was no way I was going to have time to go through that. So for those interested in like microarchitectures and so on, there's a really good publication called Chips and Cheese. And I posted a companion article to that article, to this talk on that publication. There's a QR code here. The slides will be available for everyone afterwards. And there's a link in a QR code if you're interested. In terms of me, I'm Felix, generic Canadian programmer guy wearing a flannel because it's past October and that means the flannels are out. You can mostly find me active at FCLC at mast.hpc.social on Mastodon. I'm also on Twitter for now. I'm mostly migrating my way off at FelixCLC_. And if you really have something important or critical, you can email me, first name dot last name 123 at Hotmail, because I've had that email since 2006 or 2012 or something. And then these are the two profile pictures you'll normally find me at. I do want to acknowledge some stuff. Mainly, I want to say a big thank you to people that provided quotes at the beginning. Various CPU architects, both working on x86 and working on RISC-V and working on ARM, who provided context and ideas on CPU implementation details. Once again, a spec without an implementation is useless, and implementation without a spec is also useless. You need both. Various spec lawyers, as they call themselves, who provided insights, and Chips and Cheese for hosting the accompanying article. And finally, I want to say a big thank you to EasyBuild in general for hosting me and allowing me to kind of say my piece on AVX10 and share that with the community. AVX10 in general is really exciting because it makes all of our codes a lot simpler to just say, hey, just plug in this flag once it's out, and then everything just kind of works, right? We'll go to this says closed session Q&A, but I think we're going to do a few open questions if people want those questions to be part of the recording before we go into a closed session. So this will also include questions from the live stream, for example. So if we want to open the floor, go for it.
All right. Thank you very much, Felix. This was a very great talk. Thanks a lot. If people have questions in Zoom, you can raise your hand. We will allow to unmute you so you can ask the question yourself. You can also just post it in chat, and then we will raise the question to Felix. And of course, also via the Tech Talks channel in the EasyBuild Slack, questions are welcome also for people watching the YouTube live stream. All right, we do have one question already. What does the assembly code look like for AVX10?
Identical. If I go back a bunch of slides to AVX4, when it comes to you're doing a double precision AX plus Y, it's identical. The idea with AVX10 is not to give us more things to worry about. It's to take all the things we already worry about and simplify to a single target. One thing to worry about, no more, no less.
Right, I think that answers the question. I have one as well. I have two actually. So if nobody else is coming up with questions, I can ask a couple. So one of them is you've showed the various levels, let's say, of AVX-512 up until 9. And you've also mentioned that V4 is basically AVX4, right?
Yeah, basically.
So there's a gap in terms of instructions that are supported, where the kicker is AVX9, where there's lots of, let's say, interesting stuff for HPC. Yeah. Do you have any idea how much performance you lose by running a binary that's targeting the standard V4 x86 target while running that on a chip that supports AVX9? Are we talking single-digit percentages, or could it be a lot bigger? If you say depends, you probably will, but
yeah. So no, I'm trying to avoid saying it depends. So from an instruction level for double precision math, it doesn't matter. AVX4 is equivalent for floating point 64 to AVX9 in terms of instructions, because none of the new instructions from AVX5 till 9, so all the various levels of AVX512, affected double precision, other than the first ones that said, you have it now, right? What happens, though, is implementations have changed a lot. So implementations are, you take the spec, you put it in an actual CPU. So Skylake X versus Cascade Lake versus Cooper Lake versus Ice Lake versus Sapphire Rapids versus Emerald Rapids. Those all do very different things internally. And then even within those generations, sometimes Skylake X, for example, the first generation of CPU AVX512, was notorious for downclocking. So if you normally run at, say, 3 gigahertz, running AVX1 and AVX2 codes, you would run at like 2.5 across all your cores when running AVX512, right? And because memory bandwidth was such a problem, and continues to be, the loss in clock speed overall and some memory timing issues meant that you effectively lost out on performance, and that you were actually better off using AVX512 instructions on 256-bit vectors, right? And that's changed over time, especially since Ice Lake. So Xeon third generation Xeon, whatever the marketing is for that. You basically, at most, you'll lose 1, maybe 200 megahertz on a 3.5 to 4 gigahertz chip. So it's borderline negligible at this point. So you're typically better off, but there is no kind of one size fits all, because you're not going to only be running fuse multiply adds at all points, right? And the thing is, once you jump instruction levels, that's an extra pair of bytes at the front of each instruction to decode, because you're running from SSE, then you went to your VEX, your vector instructions with AVX1, and then your EVEX with AVX512, your extended VEX, and it was yet another byte, right? So that's more instructions in your instruction stream. Doesn't matter that much. 2 bytes versus a 512-bit load, negligible, but it's yet another factor. At the same time, you have some implementations like AMD's recent Zen 4, which, if I bring, sorry.
So Zen 4 will support AVX9?
No.
Okay.
No. So I'm just bringing back to this slide here. So what happened is Zen 4 is, if you look at Sunny Cove on the left in the yellow, and then you look at Cooper Lake in the purple underneath Golden Cove, that is Zen 4, right? So you have your vectoral neural network instructions, those kind of fuse multiply add of low precision integers. And then you have your brain float 16s from Cooper Lake, which is roughly AVX, I think I have them as AVX6 and 7, respectively. So that's Zen 4. But Zen 4 has no support for actual arithmetic of floating point 16, of IEEE floating point. It has the brain float 16s, but it does not have floating IEEE floating point 16, which are actually physically different. Like, they're actually different types entirely. So that's roughly where Zen 4 is. But you'll notice that from an Intel specification standpoint, and an Intel CPU standpoint, they never released something that was equivalent to Zen 4. That was, which would have been Sunny Cove, which is Ice Lake, and Cooper Lake at the same time, right? So that's kind of where Zen 4 ends up. The other thing with Zen 4 is that they did something really clever, where they said, you know what? We don't have the die space, because we're sharing the same core across our consumer and our enterprise CPUs, to go and implement this big 512-bit vector. Because prior to Zen 4, Zen 3, and so on, that's your Romes and Milans, those were stuck at AVX2, and they never did any AVX512, right? So to go then and say, okay, we're jumping from 16 256-bit registers to 32 512-bit registers, that's a lot of silicon. So what they said was, hey, what we'll do is our integer arithmetic logic units and our floating point arithmetic logic units, or floating point units, we'll implement them as 256 bits. And then what happens is you can take the first half of your 512-bit vector, push it through, and then immediately go and fetch it and put the second half through. So some of you may be familiar with vector processors from NEC, or way back in the day, your Cray vector processors, where those would have large vectors, and then they would pipeline them into a smaller floating point units. This is the same kind of core idea. And sometimes it works really well, but sometimes if you're doing HPC only, and you're just spending a lot of time in your general matrix multiply routines or matrix vector routines, your gems and your GIMVs, then at that point, Zen 4 doesn't look so great. But for most normal people applications, Zen 4 is between fine and wonderful. And because of the power savings they were able to do with that style of implementation and some other, and a lot of like low-level compiler tweaking, you're able to get a good like 70–80% of the performance of a full 512-bit floating point unit, which gets near enough that it made sense. And then you also get a lot more cores, so performance looks better, and you also have more memory bandwidth, so that helps. So once again, it's a toss-up. It's going to be application specific. There is no one-size-fits-all, but in terms of instructions, it's the same.
All right, that was a very long answer, but
yeah, sorry, really.
No, that's fine. That's fine. There is another question in the chat, so let's raise this one from Miran. If SPR supports all of the AVX 10.1/512 instructions, will we be able to compile something with the AVX10-M arch flag or equivalent, and will it then run on SPR as well? So I'm guessing he's asking about cross-compiling.
Well, so yeah, I think it's to do with the slide that I said where it's like this AVX10, probably this one, where it's the same actual instructions. So from an instruction level, you're compatible, but the flags that your CPU ID functions check, your assembly routines to check, hey, is this instruction supported? Those are different. Now, with that, there is no reason that Intel could not issue, say, a microcode update to Sapphire Rapids and Emerald Rapids to say, hey, say that you support it, because they actually do support it. But there's kind of two factors that stop them from doing so with Sapphire Rapids and one factor for Emerald Rapids. So the two factors are, the one that's shared between Emerald Rapids and Sapphire Rapids is validation. Even though they are the same underlying instructions, before a CPU is sent out the door from the fab and packaged and so on, that design has to be verified against every instruction from every instruction set. A lot of that can be streamlined when it's the same instructions, but fundamentally, you could say that Sapphire Rapids and Emerald Rapids have not been validated from a, we guarantee this processor will work when you do X, Y, Z. On the other, and then specifically in the case of Sapphire Rapids, picture you have a cluster of Sapphire Rapids Xeons with HBM, big fancy one. And then you've gone and you've deployed that, and it's humming away doing all your matrix multiplies for your physics or your biology codes and so on. And then one of those servers, as it happens, dies. So you go up to your HPs or your Cray or your HP Crays or your Lenovo's or whichever other vendor, and you say, hey, I need a new one under my support contract, send me a new chip. The problem is then that new chip might have gotten the update to expose AVX 10.1. But all your old chips in your data center do not have that exposed. And then when someone's compiling, let's say that the new nodes that do display the flag, someone goes and compiles with march equals native, which tells the compiler, hey, check all the flags you have, because I'm going to always be running on this type of CPU. And then your compiler goes, oh, okay, sure, works for me, and embeds those CPU ID checks in your binary. But then when you go to do your big high performance LinPack run, because you're aiming for top 500, because we all love benchmarks, well then, hey, that CPU ID check that you have in your binary fails. So now you have half your cluster that does support it, half your cluster that doesn't, because also a lot of clusters, while we'll keep up with security bulletins, we're not always running the latest microcode, right? I hope that helps. The answer is, could Intel do it? Yes, but there's some certification stuff that gets in the way. And there's also some actual in-market problems to do so. So I would say from a developer point of view, treat it as a development tool. Do not treat it as strictly equivalent for production as a kind of high-level sysadmin POV. Hope that helps.
Yeah, I think that's a very clear question, a very clear answer, sorry. We have Bart who has a question. I'll let him unmute. Hi, Bart.
Hello, do you hear me?
Yes.
Yeah.
Okay, yeah, I just have a question. So at the same time as Intel talked about AVX10, they also released, they also announced APX as another new instruction set. And so I saw people talking about having a V5 level that combines the two, basically AVX 10.1 and APX. But do you know if they will come out at the same time in newer chips or one before the other?
Sorry, I have to kind of tread on NDAs are a thing. From what's been publicly stated, AVX10 is coming out first with Granite Rapids next year. APX, I do not believe, has been publicly announced for what chips it's coming on. So do with that as you will. From a high-level standpoint, when implementers and compiler folks get together for deciding what the next version 5 target will be, I personally see AVX 10.1 plus APX as being a very reasonable level. Simultaneously, though, if you look at current x86 versions 1 through 4, those assumed the AMD 64 extensions and then various instructions on top of that. So there's a reasonable argument to be made that instead of going that x86 version 5 should be APX, you can say, okay, now we're starting over again, and APX version 1, and then APX version 1 so happens to support whichever version of AVX 10 we're on at that point. APX is sort of your baseline general purpose register. What's the core CPU that is going to be everywhere, implements, and then AVX 10 is very much your high performance SIMD instruction sets for doing all your floating point math and all your integer big math units. If you're doing compute, then that's going to be an AVX. If you're doing general purpose register stuff, like a lot of normal people applications are, that's all going to be in your general purpose registers, which was covered under x86 64, also known as AMD 64, and is now going to be covered under APX. Side note, opinion on APX. APX looks really good. Clean implementation, getting rid of a lot of old stuff from the 70s and 80s that has no reason to be there in modern CPUs. It's a really nice specification.
Okay, thanks a lot. I think this is a good time to wrap up the on-stream, on-recording Q&A. And thank Felix again for a wonderful talk. For the people who want to, and as long as Felix is up for that, we can still stick around in Zoom and do some more chatting about all of this stuff. But we'll end the recording.
Actually, just before we go,
okay.
I did see one question. I'm not sure I ever caught the affiliation. Hi,
yeah.
Hi, I'm Felix. I work in software optimization targeting HPC, specifically in reduced precision. I was hoping to be affiliated with a very big institution, but it's we're now, as of today, 23 weeks into me waiting on my letter of offer after having accepted a position. So currently I am freelance and available for contracting. And also, if you have a place in your center, maybe we can chat. So officially freelance right now, no official affiliation.
All right, that's a good remark to end with, I think. Thanks again, Felix. We'll end the recording here, we'll end the stream here, but you'll probably be around for a little bit longer in Zoom.
Yeah.
Thank you very much.